Hello friends, today we will discuss an important part of complex analysis, which is classification of singularities. There are different types of singularities of a complex function. So we will discuss that how many kinds of singularities can happen to a complex function. So before going to that, we first define what is analyticity of a function at a certain point. Suppose if C to C is a complex function, okay, so this is defined from C to C, so this is a complex function. Now if Z0 is a point on the complex point C, then I will tell that I will first check that whether the limit fz minus fz0 divided by z minus z0 as z tends to z0, whether this limit, this total limit exists or not. We first find out this limit exists or not. If this limit exists, then I will say that the function f is differentiable at the point z0, and this limit denoted by f dash z0 is the derivative value of the function f at the point z0. Okay, so this is the differentiability of the function fz on z0. Okay, so first we have defined when a function is called differentiable at a certain point z0. We have to find out whether the limit fz minus fz0 divided by z minus z0 as z tends to z0 exists or not. We have to find out that at first. If the limit exists, then I will denote this limit as f dash z0, which will be called the derivative of the function fz at the point z0. And we call that the function f is differentiable at the point z0. This is the differentiability criteria of the function fz at the point z0. Okay, now if the function f is differentiable for all z belongs to a certain domain D. Now we are summarizing differentiability at a domain. Okay, so if the function is differentiable for all the point j belonging to a certain domain D, then I will call the function is differentiable in the domain D. Okay, now we come to the analyticity. Analyticity means what? Analyticity means if a function fz is analytic at a point z0, then what will happen? Then actually there will be a neighborhood of z0. There will be a neighborhood of z0. Let us define that by n z0. Then there will be a neighborhood of z0. At least one neighborhood will be there where each and every point will be a differentiable point of the function fz, which actually means that if this is our z0, we have to find out the analyticity criteria. The analyticity criteria is this: we have to find out a certain neighborhood surrounding z0. Okay, we have to find out a certain neighborhood surrounding z0 in which each and every point will be a differentiability point of the function fz, which actually means that the function fz will be differentiable on all the points belonging to the neighborhood nz0. Okay, if such at least one neighborhood exists, then I will call the function fz is analytic at the point z0. Okay, now when a function stops being analytic at a certain point, then we call this point to be a singular point of the function. Suppose if be a complex valued function, if such situation arises when the function is not analytic at a certain point z0. Okay, if the function f is not analytic at the certain point z0 and there exists every neighborhood of z0, not there exists, actually for all neighborhood surrounding z0 will contain points where at least one point will be there when the function f will be analytic. This means what? Suppose this is the z0 point. Now z0 will be called a singularity or singular point. If all the neighborhoods surrounding z0, any neighborhood you will take surrounding z0, there will be at least one point on those neighborhoods where the function f will be analytic. Okay, so first criteria is this: the function will not be analytic at the point z0. But if you take any neighborhood of the point z0, there will be at least one point where the function will be analytic. Okay, so this is our definition of singular point. Okay, so when we call a function is singular at a certain point z0, the criteria is the function will not be analytic at the point z0, and for all the neighborhood surrounding z0 there will exist at least one point. Suppose there will exist a z1 where the function fz will be analytic. Okay, so obviously the function is not analytic at the point z0, but for each neighborhood of z0 there will exist at least one point where the function will be analytic. Okay, now here comes the different definition of singularity. So now we classify or find out the different types of singularity. Okay, actually singularity have two kinds. First one is isolated singularity, and the second kind is non-isolated singularity. Now isolated singularity has three kinds. One is removable singularity. Removable means such kind of a singularity which can be removed by a suitable definition of the function at the certain point. This is removable singularity. Another is called pole. This is the second type of isolated singularity. And the third kind is essential singularity. Okay, so this is the classification of singularity. Singularity actually has two kinds, which is isolated singularity and non-isolated singularity. And isolated singularity can be classified in three different singularities, which are removable singularity, the first kind, then there exist poles, and then there exist essential singularities. So isolated singularities has three kinds, which are removable, pole, and essential singularity. So we will define them one by one. First we come the definition of isolated singularity. Isolated singularity means what? Isolated singularity means a singularity. Suppose fj, the function, has a singularity at z0, where z0 is a point in the complex file C. So fz has a singularity at z0. Now, if the situation comes like this, that if there exists a neighborhood of z0, obviously z0 is a singularity of the function fj. Now, if I find a neighborhood of the point z0 where no other singularity exists, okay, suppose z0 is the only singularity in this certain neighborhood, then I will call z0 to be an isolated singularity. So it means that this singularity is separated, is isolated, because there are no other singularities in that particular neighborhood. Okay, so that will be called isolated singularity. So to have an isolated singularity, we first must have a singular point. Now that singular point must have at least one neighborhood where no other singularities exist. Okay, that will be our isolated singularity. So for an isolated singularity, there will exist a neighborhood where there will be no other singularity other than Z0. Okay, so this is our isolated singularity. And which are the non-isolated one? The non-isolated singularities will be those singularities which are not isolated. Not isolated means, if I take, suppose Z1 is a non-isolated singularity. Z1 is a non-isolated singularity means there does not exist any neighborhood where Z1 is the only singularity on that neighborhood. This means if you take any neighborhood of Z1, any neighborhood of Z1 you take, you will find more singularities other than Z1. Okay, there will exist at least one singularity Z2 other than Z1. So that singularity will be called non-isolated singularity. So first we give examples. Suppose let us have a look. Suppose the function fz to be equal to our 1 by z minus 3. This is a function. This is a complex function, obviously. So this function has only one singular point, which is z equals to 3. Okay, in complex plane. In complex plane C, there does not exist any other singularity other than z equal to 3. This function does not have any other singularity other than 3. So this 3 will be called an isolated singularity of the function fz. This is an isolated singularity, because if I take the point 3, I can have plenty number of neighborhood of 3 which does not contain any other singularities of fz. So this is isolated singularity. And what are the non-isolated singularity? Suppose the function fz equals to log of, the principal part I have to take, the principal part log z, principal part this one. This function has infinite number of singularities. Infinite number of singularities means what? Infinite number of singularities means each and every point on the negative real axis, will be a singularity of the function log z. Okay, so since each and every point of the negative real axis, including the origin as well, if I take all these points will be singularities of the function log z. Now if I take this one, suppose this is my minus 5. If I take a very small neighborhood surrounding minus 5, then that neighborhood will contain points along negative real axis as well, and the points outer than the negative real axis as well. Those points which are outer than the negative real axis, which does not belong to the negative real axis, are not singularities. Okay, so each and every point will be non-isolated singularity, because there will be points on negative real axis as well. All the negative real axis points will be singularities. So if I take smallest of the intervals, smallest of the neighborhood, which will contain the point minus 5 as well as other points on the negative real axis as well, so that will be a non-isolated singularity. Okay, so these are the definitions of isolated singularity and non-isolated singularity. Now we will define different types of isolated singularity. Different types of isolated singularity means, suppose we take the function fz, which is equal to sin z by z. Okay, this is the function. Okay, now if I see closely, this function is defined throughout C minus 0, because this function is not defined at the origin. Okay, so obviously the function has a singularity on origin 0. Okay, so the function has a singularity on the origin 0 because the function is not defined. Okay, but if I take a close look in it, I can find that when I take limit z tends to 0, because 0 is the singularity, now I am tending z to that particular singularity and finding out what fz gives. Fz actually gives what does this gives? Limit z tends to 0 sin z by z actually gives equal to 1. So we are finding that any deleted neighborhood of 0, in any deleted neighborhood of 0, we are finding the function to be bounded. We are finding the function to be bounded. The function has a bounded nature near the point z equals to 0. So this kind of singularity can be removed. How? If I define another function capital Fj, okay, when capital Fz equals to small fz, when z is not equal to 0 and capital Fz is equal to 1, when z equals to 0, then I can say that the function fz has a removable singularity at the point z equals to 0. Okay, because now the function capital Fz is an analytic function throughout the complex plane C. This function does not have any other singularity, any singularities at all. Okay, so here we are being able to remove the particular singularity which was arising for the function small fz at the point z equal to 0. We are getting rid of that particular singularity. That's why this kind of singularity is called removable singularity. So what are the properties of removable singularity? Removable singularity are such kind of singularity which can be removed very easily. Okay, so how can we remove that? There are some particular characteristics of removable singularity. First, if fj has a removable singularity at z0, then first limit z tends to z0 fj will exist finitely, will exist in C. Okay, so that limit will exist because the function has a bounded nature, because this have a removable singularity. So the function will be bounded near the point z0. Okay. Second condition is this: if limit z tends to z0, then z minus z0 into fj vanishes. If I multiply fz by z minus z0 and take limit z tends to z0, then I will get the value to be 0. Suppose the function fz equals to sin z by z. Okay, sin z by z. If I take the limit z tends to 0 and multiply by z, then I will get what? Then I will get z will be cancelled by z, and when z tends to 0, sin z tends to 0 as well. So we are finding that to be equal to 0. This is the property of removable singularity. Okay, so removable singularity means the limit of the function fz near the point z0 will exist finitely in C. Maybe at that particular point the function is not defined, but near that point the function will have a bounded nature, and when I multiply the function by z minus that particular removable singularity and take the limit z to be tending to that particular removable singularity, then I will have a limit which is equal to 0. The limit will vanish. Okay, so this is our removable singularity criteria, and example I already have given. Okay, now I come to the second kind of isolated singularity, which is pole. What is pole? Pole means if I take the function fj to be equal to 1 by z minus 1 whole square. If I take this function, okay, we are very much clear that the function has a singularity. Where the singularity arises? The singularity arises at z equals to 1, because the function is not defined at the point z equals to 1. The function is not defined, so it must have a singularity there. Okay. Now it will be called a pole. When it will be called a pole? If I take limit z tends to 1 fj, what will I get? I will get this will be equals to infinity. This means the function has an unbounded nature near the point z equals to 1. If I make z close to 1, the function fz will tend to infinity. That means this limit will not exist in C. This will exist only on C infinity, the extended complex plane, C infinity. The function will have a limit, okay, but the limit will not be finite. The limit will be existing in C infinity, the extended complex plane, okay. So this is our pole. Now the second criteria is there will exist a natural number n. There will exist a natural number n such that limit z tends to 1, z minus 1 whole square, not whole square actually, z minus 1 to the power n, this particular n will be at the power into fz. This will be bounded. This will have a finite value. This will have a finite limit. Okay. So there will exist some natural number n. For this function, I can have n equals to 2. Okay. Then I will get what? I will get limit z tends to 1, z minus 1 whole square multiplied by fz will give what? This will give limit z tends to 1, z minus 1 whole square into fz means what? Fz is 1 by z minus 1 whole square. If I cancel out, I will get 1. So when I will be getting such natural number n such that when z minus 1 is raised on that particular natural number power and multiplied with fz and taken limit near the point, near the actual singularity, I will get a finite limit. So then I will call the function fz has a pole at the point z equal to 1. Okay, so to summarize this, I can define a pole like this. Suppose fz has an isolated singularity on z0 belonging to the complex plane C. Fz has an isolated singularity on z0. Then when it will be called a pole of the function fz? It will be called a pole of the function fz if first condition limit z tends to z0 fz, this limit will exist but not finitely. This will be existing in extended complex plane. This limit will exist for sure. This limit will exist, but the limit will not be finite. The limit will be infinite. Okay, so the actual nature of the function fz near the point z0 will be unbounded. Okay, and the second condition is there will exist a natural number n belongs to script n. There will exist a natural number n such that when limit z tends to z0, I will have z minus z0 to the power n multiplied by fz. This limit will exist finitely. Okay, so this is our definition of pole. Okay, and the smallest positive integer, the smallest natural number n for which this limit is bounded, this n will be called the order of the pole. Okay, so the smallest positive integer n such that limit z tends to z0 of z minus z0 to the power n multiplied by fz is a finite complex number is called the order of the pole. Okay, so this is our pole definition. Okay, now I will define the third kind of isolated singularity, which are essential singularities. Essential singularities. Singularity. Essential singularity means what? Essential singularity, a function fz will have essential singularity at a point z0. The function fz will have an essential singularity at a point z0 if first condition 1, z0 is an isolated singularity. Z0 is an isolated singularity of fz, the first condition. Second condition, limit z tends to z0 fj does not exist. This limit will not exist. Okay, so this is our essential singularity. So the function fj will have essential singularity at the point z0 if z0 is an isolated singularity of the function fj, and when I take the limit z tends to z0, the function fj will not give any particular complex number. So this actually means the function does not have any unique limit when z is tending to z0. To be more precise, let us take an example. Let us take an example of essential singularity. If I take the function fj, the function fj equals to e to the power 1 by z. Okay, this is the function. Clearly we can say that z equals to 0, is a isolated singularity of the function e to the power 1 by j. Okay, so this is a isolated singularity. Now if I take the limit, z tends to that particular singularity 0 as fj, then I will get what? I will get three distinct values. Well, if I approach z, if I approach the origin 0 from the along the right of real axis, means what? I will take z equals to x plus iy first, then I will make y equals to 0. Y equals to 0 means case, y equals to 0 means z is tending to 0. If I make y equals to 0 and x tends to y equals to 0 and x tending to 0 plus, this means what? This means the z is approaching to the origin 0 from along the real axis, along the positive real axis. Okay, so then I will get what? Then I will get fz mod. Fz mod is equals to e to the power 1 by z mod. This will give e to the power 1 by x mod. This will tend to positive infinity when x is tending to 0 plus. Means what? Because when I take x to be near 0, then 1 by x will be a very large number. Then e to the power 1 by x will be a very large number that will be tending to positive infinity. Now, if I take the second case, if I make y equals to 0 and x is tending to 0 minus, this means what? Z is approaching to origin, but from the along the negative real axis. Then this gives what? This gives fz mod gives e to the power 1 by z mod. This gives e to the power 1 by x mod. Now, if I take x to be near 0, but it is a negative number here because x is approaching to 0 from left. So, x is a negative number here. So, 1 by x will be a large negative number. So, e with a power to a negative real number means 1 by that particular e to the power that. So, that will be tending to 0 for sure. So, we are finding two different limits for the approach of z to the point origin, from two different paths. So, we are getting distinct limits, and therefore, we can say that this limit does not exist in C infinity. Okay, so the function fz has an essential singularity at z equals to 0. Okay, so this is our three distinct types of essential singularity, pole and removable singularity. Three distinct types of isolated singularity. Now, if a function fz has isolated singularity at z0, if function fz has an isolated singularity at z0, then it must have a Laurentz series expansion in a deleted neighborhood of z0. That Laurentz series expansion will be like this. Fz will be equal to k equals to minus infinity to plus infinity ak into z minus z0 to the power k, where ak is actually equals to 1 by 2 pi I integration over a closed curve C actually a circle where this will be like this, f tau by z minus, like this, I will write this like this, fz by z minus z0 to the power k plus 1 dz. This will be the coefficient ak, okay, and C will be a closed circle belonging to the region z minus z0 is greater than 0 and less than some r. This is a real number, obviously positive real number. So the circle will be remaining on this particular region, okay. So this have a Laurentz series expansion like this. Now if I expand this, I will get what? I will get, first I will get the negative powers, like k equals to minus infinity to minus 1 ak z minus z0 to the power k plus k equals to 0 to infinity ak z minus z0 to the power k. Okay, so these two portions are there in a Laurentz series expansion of a function. Now this portion, the negative power parts, this is called the principal part. This is called the principal part. This is called our principal part of the function fj, and this is called the regular part or holomorphic part or analytic part. Okay. Now, when this principal part actually vanishes, when this principal part does not exist, then I will call the function fj as a removable singularity at the point z0. If the principal part is finite, there are finite number of coefficients which are non-vanishing, then I will call the function fz has a removable pole at the point z0. And if the principal part is infinite, that means there are infinite number of negative powers of z minus z0 terms, then I will call the function fz as an essential singularity at the point z0. Okay, so this is my definitions of removable singularity, pole and essential singularity based on Laurentz series expansion. Okay, so all we have for this is all we have for today's discussion. Thank you. If you like the video, please give some feedback, and thank you.